schakelen.
De rest wel dadelijk wel.
Goed. Dames en heren, dit is de eerste versie van circulaire economie, waarin we dus als regio Limburg van KIVI gewag willen maken. En de Universiteit van Maastricht heeft sinds 2018 een faculteit, een beta-faculteit, die heet dus Science and Engineering FSE. En die werkt vooral internationaal. En er zijn op het ogenblik iets van 3150 studenten, alles bij elkaar, zijn daar bezig met allerlei onderdelen van dit vakgebied. En ja, we willen dus daar ook wat meer bericht aangeven dat die studentenopleiding is gestart en dat de eerste bachelors zijn afgestudeerd en nu met hun masters bezig zijn, maar daarnaast ook al studenten bezig zijn met masters of met hun PhD om bepaalde onderwerpen verder uit te diepen. Voor veel mensen is dat niet bekend dat daar een beta-faculteit is. Maar goed, dus dat is dus. De presentatie zal verder ook in het Engels plaatsvinden, omdat een aantal mensen dus in het Engels willen alleen maar met elkaar kunnen praten. Dat is vooral in Maastricht, is dat standaard. Dus ik zal dadelijk overschakelen naar het Engels. 20 jaar geleden, toen werkte ik bij het Nederlands Energieagentschap van Economische Zaken. En daar hadden we het over ketenbeheer en lifecycle analysis. En ik dacht van ja, dat is niks meer, maar tot mijn grote verbazing is er nu een Europees platform over LCA. European Platform for Lifecycle Assessments. En dat is binnen het Europees Parlement goedgekeurd als wetgeving. Dus alle bedrijven moeten daar vanaf 2030 aan gaan voldoen. Dus er is nog een hele klus voor iedereen om daar iets mee te gaan doen. Dus het is een bijzondere ontwikkeling. Zelfs accountants moeten straks voor bedrijven nog een maat gaan nemen over milieu-impact van hun project van hun product in de maatschappij. En ja, dus daar zit nog al wat ontwikkelingen aan te komen. En I am starting now in English. This webinar is the first in circular economy for the KIVI region Limburg. And we have a connection to the University of Maastricht in the Science and Engineering, the beta faculty of Ingenieurs. Where about 300 students now are acting and doing their studies. And the next point is that we start with plasma technology, and plasma technology is a wide idea about plasma from plasma burners to plasma fusion of so the achter project is looking to the plasma fusion technology. So that's a wide system of thinking in technologies. But Hans Linden is speaking about a specific subject of plasma technology for looking to reuse new materials in the circular economy to exchange the oil and gas industry. This lecture is also made a video so that you can see afterwards what was discussed about it. Hans Linden is the manager of the Plasma Lab of Brightlands in Geleen, and maybe I will give you the scene on to tell about what you are doing about plasma technology.
Certainly. Thanks for the kind introduction, Theo. First, I want to introduce myself a little bit. I'm Hans Linden. I'm employed by TNO, but work in a collaboration program which is called Brightside, together with Maastricht University, the SciTech Services, which is a company on at Gemmelot, and the Brightlands Chemical Campus. We work there together with the chemical companies and trying to realize the goals of 2030 and 2050, the climate goals, helping to develop the processes which are necessary that we reach those goals. What's my role in the whole is that I'm the program manager of the electrification program within Brightside. And within this electrification program, we dedicated our work to the use of plasmas. Plasmas, actually, you could see it as an electrical flame, as Gerard van Rooij it always calls. It's a flame which there's no CO2 being produced, but still you have the energy to get reactions going, which are necessary in the chemical industry. Little bit about the partners. SciTech Services is a service provider at Gemmelot. They do the services for the chemical companies, the turnarounds. So if every factory goes down after, for instance, 4 years, they tear them down, refurbish everything, and build them up again. And these kind of things is what SciTech is doing. TNO, I don't think I have to introduce that. It's the biggest contract research organization in the Netherlands. Maastricht University was already explained in detail by Theo Nulmans. At Maastricht University, Professor Gerard van Rooij, he's heading this part, and he actually initiated the plasma lab, which will come back on during my presentation. And then, of course, the campus who really helps us establishing the laboratory and a later scale, probably also the larger production. Okay, where are we situated with Brightside? We are situated at Gemmelot, and on the left picture you see Gemmelot, and you also see the yellow part, which is the campus, and we are situated at the campus. In the past, the Gemmelot was just one company, was DSM, but by now it's more than 50 producing chemical companies, and they all interconnected with each other. So the product of one is the feedstock of the other. The waste heat of one company is the heating for another company. So they're all connected to each other. And the campus is a special part. There's where the R&D takes place, where Fontes is situated, for instance, Fontes Zuid is situated, Hogeschool Zuid, where university is situated, but also the startups, the pilot plants. That's where the new things are happening, which then when they're ready, they can go to the industrial park. But the chemical industry, actually, they have quite a challenge. They have to meet the climate goals of 2030 and 2050, and for this, new processes are necessary. Of course, a lot of those already being done, and we try to help them with this. And it's not only for Gemmelot. We are inspired by Gemmelot, as we say so, but we also work together with companies outside of Gemmelot. So if you look to what has to be done in the chemical industry, The electrification, of course. We have to electrify what can be electrified. I come to that later. That's my second point. We have to maximize the energy generation without CO2 production, so wind, solar, maybe nuclear, at least so that we can avoid the greenhouse gases going into the atmosphere. Prioritize on the energy efficiency, and what's also very important, to look to alternative feedstock. And in the future, we cannot use any fossils anymore. And how can we do that? And that's will be my first part of the presentation. So actually, what we do also at Brightside, we also do modeling. We calculate how to reach the zero emission at 2050. We have a model where the different technologies can be chosen by the model, so that we can calculate how much CO2 reduction and CO2 emission can be realized. So on the left graph, the blue part is what already has been realized, and the green part, which is calculated using the different technologies, using the different the adaptations at the chemical side. For this, we every year make a small booklet, which is called the Brightside Transition Outlook, where we really describe what's all necessary. If you're interested, you can download it from the internet site, from Brightside, just to have a little bit an idea about what's all possible. Realize Gemmelot is one of the largest CO2 emitters in the Netherlands. I think after Tata, it's the second biggest. So it's very important that we make those steps. And as you already can see on the left picture, we are already pretty well on our way. We are really already making big steps there, so that we can meet the climate goals. When there are already questions during my presentation, just put them already in the chat, so then they will forward it to me that I can directly respond to those. So if you look at Gemmelot at this moment, I give this an example, but for the other chemical sites, it's a little bit the same. At this moment, natural gas goes in, naphtha comes in, all via pipes. We have all the factories at Gemmelot, and then we produce the fertilizers, the polymers, the other nitrogen containing products, and we also make quite a bit of carbon dioxide.
Sorry to interrupt you. We have a short question from Arjan, and he's asking, but how much progress is the result of stopping activities?
That's not up to now. That was not because of stopping. That because the changes made by the companies on the side. It's not because of stopping. Of course, there's a lot of debate about stopping, but I think we should not aim for that. Realize in Europe, 1 million people work in the chemical industry. Please, there's a lot of our income in the Netherlands also comes from the chemical industry. We should not throw that away. We should see how we can adapt the processes that we comply to the climate goals, and that we still make the products we need. Everybody has in his house several products coming from which has their origin at Gemmelot. So we should be very we should be careful with that. Don't give it away. So this is the situation at this moment, and this is how the situation can be in the future. So there we start with renewable electricity. We have a different feedstock, which I will explain a little bit more about later on. We make it the same products, and by the mechanical and chemical recycling, we have one part of the feedstock, and we have some other ones which I'll explain later. And actually here you can see those. You can use sugar, for instance, from sugar beets, hydrogen made by electrolysis. You can use CO2 out of the air as a carbon source, and of course the recycling from plastic, and there you have the last carbon source. So for the carbon, we have three sources: we have the natural resources, recycling, and CO2 from the air. And hydrogen we can make with electrolysis. And then we can really go into to a circular way. Why do I show this picture? With 3 of those, the plasma technology will also is important. I show you how we can make hydrogen using a plasma, how we can do plastic recycling using a plasma, and how we can go from CO2 to also to the new feedstock for the chemical industry. So we have to stop using the fossils in the future and look to different resources, like the sugar beets, like the CO2 from the air, like the hydrogen from water, and of course recycling. And that's how we also at the end get to a circular system. Oh. This brings me to the second part, and this is about electrification, and that's where we use the plasma. We think with plasma we can really have a game changer. It's actually it's an old technology which I will show now. First, a little bit, what is a plasma? Actually, everybody knows a plasma. If you have a lighting, it is also a plasma. It's a discharge. And then you also know that in this discharge, there's a lot of energy. And this is the energy we are using to drive reactions. You see that especially when you have chemical reactions which normally need a lot of energy, endothermic reactions, then there you can make the difference with a bit of plasma. There are also already applications used in the industry, for instance, for welding, plasma welding. If you look to your glass panes in your house, the low E glass and the HR++ glass, they have all kind of coatings on top, and these coatings are also applied by a plasma process. You see this on the right corner here. It's a sputtering process. It's already done on a large scale. Glass panes from 6 by 3 meters go through this machine, and they are coated. There are different coatings on top of each other, and these coatings, they reflect the infrared light, but they are still transparent. So you have your light comes into the house, but your heat stays in the house in the summer, or you keep the heat out inside of in the summer, and in the winter you keep the heat inside. Another application is for neon lighting, also plasma. So actually, plasma is already being used on a large scale. One of the molecules where we look at is methane. And also, and actually, they have been looking at methane already for a very long time. Why do we want to look at methane? If you look to the chemical industry, where the greenhouse gases come from, then you have the ammonia plants, and the ammonia plants, the methane goes in. Hydrogen is produced. From hydrogen you make ammonia. From ammonia you go to the fertilizers. So that's a pretty important step. But for the production of this hydrogen, to make the ammonia and to make the fertilizer, for each ton of hydrogen you produce, you also produce 9 tons of CO2. So there's a huge amount of CO2 being formed. Another large part of the chemical industry are the naphtha crackers. And therefore, each ton of olefin, the basis for many plastics, you also produce 1 ton of CO2. And with methane and a plasma, we can find a solution for both of those CO2 emitters. So on the right side, you have a naphtha cracker. At this moment, the naphtha goes in. In the future, that will be replaced by bio-naphtha or pyrolysis oil. And in the future, it will be driven by electricity. At this moment, they are heated with natural gas and by methane being formed in the naphtha cracker. But there are big programs in the world to electrify those naphtha crackers. But 15% of the naphtha becomes methane. And at this moment, this is burned directly to heat the cracker. And if you electrify the cracker, this methane is a waste product. That's exactly the waste product we want to use. Put the waste product in the plasma. Then you can make acetylene or ethylene. And this can go back to the naphtha cracker. And you can make hydrogen, which can go to the ammonia factory to produce the fertilizers. Then on both factories, you do not have any CO2 left. We need extra natural gas. I forgot to put it in here. So that we really can, for the whole site, we can. There's enough feedstock to produce the fertilizers and the plastics, but there's no CO2 emission anymore. So with plasma, actually, this is an efficient way to start from methane and going to hydrogen, acetylene, and ethylene. Acetylene is the basis to make ethylene, but via hydrogenation you can go to ethylene. But from acetylene on, you also can make, for instance, PVC. You also can make benzene. So acetylene is a building block for the chemical industry. And with this plasma, we do not have any scope 1 CO2 emission. And it is an old technology. It's based on the Hulse process. I come to that later. It's already developed in the 30s last century. A plasma is an efficient way of heating because you heat the gas. It's not that you heat through a wall. So your heat is inside the plasma. The methane goes in the plasma, and there the reaction takes place. So there's no heating from outside. It's all from only in the inside. It's also possible to switch it on and off very fast. When the plasma starts, within a second, you have thousands of degrees inside of the plasma. And that makes it also possible then to go to intermittent operations. So at times that was abundant green electricity available, then then you operate. And why do we want to use the plasma? If you a little bit detail about with some chemical formulas, the top line is actually the steam methane reforming process as being used in the chemical industry at this moment. And to produce there 1 kilogram of hydrogen to make the ammonia and to make the fertilizers, for instance, then it takes you thermodynamically seen 32 megajoule of energy. And next to the hydrogen, you make 5.5 kilograms of CO2. And of course, you can do CCS. There's also big projects for this going on. Portals in Rotterdam and also in Antwerp, they have a big project to take away the CO2 and put it in the ground. The electrolysis to make hydrogen, a lot of attention for that at the moment. It will also become very, very important because we're going to use you're going to need a lot of hydrogen in the future. But we have to realize it costs a lot of energy. Compared to the steam methane reforming process, it takes 142 megajoule to produce 1 kilogram of hydrogen. And next to that, you produce 8 kilograms of oxygen. And this oxygen, most of the time, it just goes into the air, but it would be much better if you also could use the oxygen. For some applications, for instance, in the steel industry, that really make sense because they also need oxygen. And we compare it with the plasma technology. If you start with methane, put it in a plasma, you can make hydrogen and carbon. Then it only takes 19 megajoule for 1 kilogram of hydrogen. And if you make hydrogen and acetylene, which I explained already before, then it takes 63 megajoule, double the amount of the SMR process, but you have 2 products. You make 1 kilogram of hydrogen and 4.3 kilograms of acetylene, the basis for 8 polyethylene. I will come to that later about the carbon. One moment. It's my next slide, actually. So to make hydrogen and acetylene starting from methane, it's developed in the 30s last century in Germany by the company Hulse. At that time in Germany, there was not, they developed that And you see here on the middle a picture of the plasma device itself, which has been used from 1939 until 1993 to convert methane into acetylene and hydrogen. This factory it was a factory built for that in the 30s. It was refurbished in 1993. By that time, it was owned by Evonik. In 2019, this factory was sold to Ingenieurs, and it's still operational. It's an old technology used only in one factory in the world. It never became bigger because it was far more easy to burn natural gas than to further develop the plasma technology. And that's why it was not used at more places. But it's very reliable because it's still functioning. And it already were quite big systems they had. This system had, it says here, 7,000 kilowatt. But we know from people who work there, they got up to 10 megawatts. So that's 10,000 kilowatt. And this was just one system. And they had several of those, 12 next to each other. Actually, the left picture you see, this is from a report which you can find on the internet. It's when in 1945 the Americans got into Germany and they made reports of all the factories in Germany. And this is from this report. So all technology. Then coming to the carbon, that's also being used already. If you make carbon and hydrogen, you can make if you have a good grip on the process, you can make very good carbon black. And this carbon black can, for instance, being used in tires. So Monolith, a company in the United States, is already doing that. They use the plasma technology to convert methane into hydrogen and carbon black. One factory they have running is on the left side, and one factory they are building at this moment. Last year they got a loan from the DOE in the United States of 1.1 billion to build this next factory, because it's an efficient electrification process, electrified process. But we also have to realize that the carbon black market, it's limited. It's a 10 megaton annual market. And with one big chemical site, you already could produce enough carbon black for the whole world market. So that's not the need for carbon black is not high enough. That's why we want to aim at acetylene and ethylene to become so that the carbon stays in the loop. And if you only make a very low value carbon for landfill or for something like that, then the carbon is out of the loop. It has to stay in the loop. Does this answer the question about the elementary carbon? Okay. And then the next atom where a lot of work is being done about is nitrogen. And that's even an older technology using a plasma. In 1906, there were two gentlemen, Birkeland and Eide. They developed a process using arcs to make nitrogen oxide. And actually, that's was used for the fertilizer production. By that time, there was it was not enough chili saltpeter available. That's why they developed a new process. They did build a factory with 32 arcs of 750 kilowatt. And it was situated next to a waterfall power station. That was necessary. There was not so much electricity in that time. And that was the only way to how they could do this. The process was surpassed by the Haber-Bosch process, but now there's renewed attention for that. But, one example of that is Vital Fluid. It's a company in Eindhoven, scale up, and they produce actually the equipment to produce NOx on the solid in the water on a small scale. Why do they use why want to build this equipment? This is for greenhouses. And so they can make NOx dissolved in water as a fertilizer, which can directly be fed to the plants in the greenhouses. So then you don't need a big fertilizer factory. It's just you can make the fertilizer on demand and specific for these plants. Plastic waste, also already mentioned in the beginning. And actually with the plasma, I explained that you can go to very high temperatures and that it heats up very fast. And when you put plastic waste in a plasma, then it heats up very fast to this very high temperature. That means that you end up in the top part of this overview. It means that you make quite a big amount of gas compared to the oil and the char. And this actually, we want the gas because that we can use again as a feedstock. We do not want to make char as less as possible. And also oil, it's not that easy to handle. With gas, that's easier to handle. And that's why we can really make the difference using a plasma. Also, there are some companies are starting up now. This is a company in the United States. They use a little bit different waste, but they make only hydrogen. I will not use for that, but it's good to see that at least these technologies are being explored at this moment. And the fourth one, the last one, which I will explain, is CO2 utilization. And also there, it's already been researched for quite some time, especially in Russia by this Mr. Friedman. He's a very well-known professor on this topic. I spoke to him a few months ago. He's already working on this for a very long time. And there, the CO2 from CO2 you can make CO, and CO from CO on you can, for instance, make a methanol. There are several. CO is again a feedstock to make several of the chemicals we need in the future. And also there you see the first startups. This is a startup in Antwerp. They try to also to bring this to a larger scale. Now, a little bit what are we doing at Brightside? We work with those partners, SciTech, University of Maastricht, and TNO together. And actually, why do we want to do this with these three partners? In this way, we can use on a very large TOL scale in parallel with each other. So we can do the low TOL work, which is with the main emphasis at the University of Maastricht, really understanding the plasma, measuring on the plasma, seeing where is what being formed. And we started with the methane for these three, but it comes to that later. The second part is the bench scale systems, TOL 4 to 5, bigger systems, and there we also use arcs besides the microwave which we are using on the left side. Here you see a small picture of the plasma inside of one of the plasma systems, and there we define much more the process as it can be used in the industry. And the next steps going to TOL 6 to 7, where SciTech is much more in the lead. In the middle is TNO is more in the lead. There we want to go to 500 kilowatt to demonstrate it at a reasonable scale, at a 24/7 scale, so that it can be transferred to the industry. This we will do actually in a separate company, because quite some investment is needed to make this step. So for the lab scale experiments are running at this moment. The bench scale experiments are running. We do all the engineering and things like that is for the pilot plant already, and we hope to can start building the pilot plant for methane valorization next year. So this will be operational, in a short time now. And this is what we call our plasma lab. These three steps. From there on, it can go to a demo phase and to large scale production. A little bit also about the kinetics. If you put methane in a plasma, then you make first CH3. Two CH3s are coupled to ethane. From ethane it goes to ethane. From ethane it goes to acetylene. From acetylene it goes to carbon. And to get this reaction going, that's not that difficult. But to stop the reaction in time, that's a challenge. Here on the x-axis you see the temperature. On the y-axis you see the rate, reaction rate coefficient. And when you leave the methane long enough in your plasma, you make carbon black and hydrogen. Of carbon and hydrogen. Carbon black, then you need to really have to do a very good grip on the plasma. If you stop the reaction in time, you have the Hulse process, as I explained. Then you make acetylene and hydrogen. And when you could even stop it faster, you can make ethylene and hydrogen. And ethylene, this is the basis for the polymers, for many polymers, as I explained. So that's it would be very good if you could make directly ethylene. Then it costs less energy, and we have direct the feedstock for making the polyethylene. Because we are using a plasma, we also think we have some non-equilibrium effects, meaning that we have an enlarged process window. On the picture, you see also an example of a plasma just between two electrodes. It's a Jacob's ladder, but this arc goes up. But if you want to visit us, then we can show this. So this is our timeline for the methane. So we already working on the lab, we are working on the bench scale, we are establishing the pilot plant. So that means that there will be a demo plant before 2030, and that the commercial plant will be there between 2030 and 2040. Methane is the first step. We already started now also with nitrogen fixation. With CO2 and plastic recycling, we do know the first initial experiments. One of the projects we have running, I will just mention separately. So it's a NextGen project. NextGen is one of the Groeifonds initiatives within the Netherlands. And NextGen aims at actually to develop the high-tech industry even further. We are very strong in the high-tech industry, so that we develop the equipment which can be used for several applications. So also for plasma. So there we work in a consortium with 14 partners, mainly out of the high-tech industry, next to a few end users of the chemical industry, to develop the equipment necessary for this. In the chemical industry, the high-tech equipment was not used on a large scale, and here we bring those two industries together, so the high-tech industry and the chemical industry. So that we also have the equipment for large-scale production available by the time also the processes have been developed. Then we're going back to the circularity. On the left side, you have a picture of what happens now. Naphtha gets in, natural gas gets in. We produce the fertilizers and the plastics, and we make CO2 on different places. We think in a different way how the methane goes into the plasma, using, of course, green electricity, produce the fertilizers and the plastics without CO2 emission, and from the byproducts, the plastic recycling, from the biomass, we have our methane source to make it circular. That's how we...
Sorry to interrupt you again.
Yeah.
We have another question from Arjan, and he asks, so the pilot plant serves to bring the Hulse process further to make ethylene rather than acetylene.
Yeah, the pilot plant, we still aim at acetylene and hydrogen. And what we do is there with the knowledge from nowadays and with the equipment available nowadays, we think we can do better than the factory which is already there. And actually, you cannot buy the Hulse process. Of course, it's operational, but you can never buy it, nowhere buy it. And that's where we aim at.
Thank you. And then we have another question from Vincent.
How does the technology cost scale and capex? And rather linear way? No, not linear. That's not fully. What we do in the NextGen high-tech project, where we define the unit size, the optimum unit size, and that will be placed next to each other, so it will be modular next to each other. As also what I showed what was happening in Mall, they had 14 arts or something like that. So there we want to define which is the optimum. So and when you start putting them next to each other, then it becomes linear. But before that time, it's not linear. And actually, I think that was my last slide, so I'm happy to answer some more questions.
Thank you very much, Hans, for your presentation. Are there any other questions? Also allowed to use your microphone if you want to ask Hans a nice question.
You also feel free to contact me if you have questions afterwards. My email address you see on the screen. Just send me an email, or if you think if you come up later with a question, do not hesitate to contact me.
Any questions for now?
Maybe ask a question right away.
Vincent, go ahead.
How does the technology work with changing input compositions? So let's say the gas composition going in changes because the process before changes.
It depends a little bit on what are the pollutants. If you for the hydrocarbons, we don't mind, because actually you can see the plasma as a big hammer smashing the molecules. But if you, for instance, if you have sulfur inside, these are the things which you do not, which you try to avoid, because they also react. But that's also for the other processes, of course. So it depends a little bit on what's in there. So everything with carbon and hydrogen, we don't mind. Oxygen also not too much, but nitrogen, sulfur, these kind of things, that's not so nice. For instance, from nitrogen inside the plasma, you can make HCN, and that's something we do not want, of course.
No. Okay, great, thank you.
Theo, you have a question?
I am just wondering how we can help the fertilizers for the farmers to reduce the nitrogen production.
How can we use what we could do is what we also look at is not for the nitrogen, but we do also use look at biomass and biogas. Sorry, and this we can also convert into, for instance, CO and e-methanol. For the nitrogen, I think making the fertilizer dedicated, like Vital Fluid is doing, I think that's also a very nice way. So that we do not, that we have the nitrates just enough for our as a feedstock for as a fertilizer for the farmers.
We have one question in the chat, two.
Yeah.
The first is from Freek, and the question is, will be there enough biomass to feed chemical industry 2.0?
It's a combination. It's not only biomass. It's what I explained with those three pictures. So we can use the CO2. We can use the suikerbieten, sugar beets, and of course and biomass. So we have different options there, and we have to use them all. So that we have enough feedstock.
And then we have another question.
Can you explain how you can? It's already being done. Also, actually in India, there are quite a bit being done. It's what you normally do is that you do some pre-treatment, so that it can be put into a plasma, and so to make the hydrogen and the hydrocarbons. Pre-treatment is necessary, and also to some extent, you also have to sort the base. You showed the advantage of plasmas versus electrolysis. Does Arie de Vries, is there also a question which I have to answer? And about plastic recycling is usually a very energy-intensive process. Yes, with a low yield. Will it work? Yes, it will work because it's being done in India already. Can use a supply of carbon black for that. Yeah, that's also a very good question about the carbon black. That's where several of the startups are aiming for. So the carbon black for the batteries. But for the bulk processes, as in the chemical industry, that's still a small market. And there's quite some methane will be left over from the naphtha crackers. So there should so for part of it will be used for that, certainly, and that's also a very good option.
Hans, Arie is
okay.
Holding his hand high. So Arie, maybe you want to ask your question with your microphone.
Do you hear me?
Yes.
We can hear you.
Sorry for the part of the message or the question. My question actually was in the large scale hydrogen economy, would be plasma a real contender, because both systems, electrolyzers, large scale electrolyzers versus this plasma technology, it appears to be really a large advantage.
No, there's room for both. What we look at is as hydrogen as a feedstock to make products, and the hydrogen used for all other applications in our energy transition. It's the materials transition that the electrolyzers will be very important.
But very energy consuming.
Yes, but still, it's also not at a certain point. Also, the methane is there's not enough methane, so we really need both. We should not for each. There are different solutions necessary also. So the methane we have as a rest product, so we have to valorize it. But next to that, we also have to have much more challenges where we need hydrogen, and so that's.
Okay, thank you.
Then we have one other question in the chat. What is the S specification for methane as a feedstock?
What specification for methane? Actually, we know, for instance, for the system in Germany, they used different feedstocks there, so it's not very sensitive to it. So as long as the majority is then, of course, the methane, but the exact specification I don't know by heart. We have this information, of course, but I don't know that by heart. Yeah.
I think that were the questions for now in chat, at least. Then I think, Theo, I give the word back to you to thank our speaker for today.
Yes, Hans, thank you for your presentation about new technology, plasma. And I have written that also plasma could be used as a storage material for energy. So there is probably another possibility in the future. And I hope we have started now with circular economy, the subject about plasma technology. next time we think we are looking at waste recycling, and another one is using new building technologies to make buildings sustainable, and also materials. So we already have 3 subjects now for circular economy, and I hope if somebody is listening and he said, well, I have a subject for the next time, he can send it to me. Thank you, Hans, for your presentation, and it was a very good idea to see what Gemmelot is and Brightlands is doing on this material side. Thank you.
Okay, thank you. You're welcome. See you next time. Bye-bye.
Next time.
Thank you and have a nice day.